Hi everyone, I'm here to present our third project, which is on physics-informed max-stable spatial processes for inference in regions with no observations. And in this project, we're interested in incorporating the underlying physics of a phenomenon into the spatial dependence of a max-stable process. So to start off, we're going to have some background and some motivation. And what ends up happening is that we want to characterize extremes over infinite dimensional spaces, which is important in many disciplines such as climate, material, finance, and in public health. All of these have different applications, but the difficulty is that data in these extremes are rare, so we need to use some sort of spatial correlations to try to inform these rare events. And our question is, how do we describe these distributions from limited data? And here we have a figure from this paper that describes how that looks at a region of the US where we have some extreme data. And so the interesting thing is many of these disciplines consider models that are used to describe the behavior of the underlying phenomena. So for example, in weather forecasting, we have numerical methods that extrapolate and try to predict the weather over the next few days. And we have PDEs that describe the stress of the material undergoing some stress or some sort of deformation. Financial models that describe derivative prices. And our goal is to describe these descriptive models, which are generally operating in the bulk or in the normal behavior of the distribution, with the extrapolation theory of max stable processes and extreme value theory to try to extrapolate to the extreme regimes. This has been done in kind of an ad hoc fashion by a number of different researchers. So in one case right here, we have these finite element simulations, which are come from some sort of finite element simulator and try to predict the crack propagation in the material. What ends up happening is that these strains are then fit to some sort of Weibull distribution that varies over space, is used to then predict the crack propagation. So what we want to do is we want to, instead of considering these as two separate steps, we might want to combine them into one framework. And that's the purpose of this project. And our focus is going to be on linear elliptic and parabolic PDEs. And these PDEs are particularly amenable because they have this structure such that they're easy to define through this matrix, which is known as, in terms of an SDE, in terms of the diffusion matrix, and this matrix here, which is known as the drift matrix. So these kind of describes the level of dispersion of the object that we're interested in, and this kind of describes the expectation or how the object is propagated forward in time. So what we want to do is we want to assume that this model exists, and this has some applications. And for example, the heat equation is one equation that satisfies this data. And we want to consider how we can impose the knowledge that this exists into our max stable process. So to give a reminder of what the max stable process is we have this component. It's given by this spectral decomposition, which is the max of an infinite number of samples from this JN, which is the spectral measure, and this AN, which is the nth arrival unit rate Poisson process. So what's interesting is that this JN gives you something that describes the spatial correspondence and the spatial dependence of the extremes. And this is powerful because it allows us to make a statement about how X, wherein it's within some local neighborhood, how it should behave. And this AN describes how intense or how strong the particular realization is going to be. And the finite dimensional margins correspond to multivariate extreme value distributions. So the methods that we described for fitting multivariate extreme value distributions would apply to these finite dimensional margins. So now to get to our main topic, we're going to talk about these physics-informed max stable processes. And in this scenario, what we have is we have some boundary data, which is collected on a boundary over some time scale, and we have already fit a max stable process over this boundary given this maximum data. But the issue is we don't have data on the interior of the domain. And what we want to do is we want to use the underlying knowledge of the physics to try to interpolate on the interior. So we know that the data on the interior should satisfy this differential operator at A, and we want to actually incorporate the knowledge of this max stable boundary. So to give an example, we have the heat equation here, which is given by this second derivative term evolving over time. So we want to study the maximum of the solution over long time horizons and extrapolate over long time horizons. What might be a decent assumption to make is that this spatial derivative with respect to, or the temporal derivative may be increasing over time. So we have the relation that this function, the second derivative for the Laplacian of this function is increasing over time. And this suggests that U should be a subharmonic function. And so we have these sort of constraints that we want to impose on our max stable process such that we can encode it with the physics and also encode it with the also incorporate these statistical properties of the extreme value theory. So we want to consider the maximum of this U of x such that this U of x is a subsolution to this differential operator A. So the generalization of the subharmonic function would be the subsolution of the elliptic operator here. U is also max stable. And then U is bounded by the boundary data is less than or equal to the boundary data. So 2, we motivated in the previous slide by saying that in the future, maybe these things will be increasing over time. And 3 requires that we actually have the statistical extrapolation capabilities of extreme value theory so that we know that we are extrapolating correctly. Finally, 4 maintains that the solution is consistent with the boundary data. So the data that we've actually fit to the distribution makes sense. And we formalize these optimality conditions in this theorem, which basically says that if we have a max stable process is given by this U, the spectral measure given by Hn, then if Hn satisfies this PDE, then this will be both the largest max stable process with the de Haan representation such that this property is satisfied. So the U is a subsolution, and this property such that the data is less than the max stable the solution is less than the max stable process on the data, on the boundary, is also satisfied. And so to give an idea of why this makes sense, we have a closer look at what this Jn is right here. And in the full case, we also call it the H function. This controls the spatial dependency of the max stable process. So we want this to both, again, satisfy the extrapolation properties and in some sense satisfy the PDEs that govern the data. And this is easily achieved by doing this A of j equals 0, while also after taking the max, we get something that looks like a subsolution of the PDE. And again, we want to maintain these sort of properties such that the data on the interior is no greater than the data on the boundary. And this may be motivated by the fact that we can collect data in regions that are very important to us. And we might be able to find which regions have the most extreme data. And the max stable process should also give us the maximum coverage so that we are properly extrapolating to the extremes according to the extreme value theory. But we note that even though we have this solution, is not going to satisfy the PDE exactly, because by the max operator, even though we have this that's satisfied exactly, the max operator will destroy this over the full domain, since multiple functions may contribute to the PDE, to the max stable process itself. So to characterize how the PDE is satisfied, we define a weak solution. And this weak solution is given such that for almost every X within our domain, and for some epsilon, there is a ball of radius epsilon centered at this X where these solutions of the PDE is satisfied exactly. Now, we might want to consider how these regions are connected or how the topology of these regions might be. So we place a few assumptions. So we can do this in a relatively interesting way if we place some assumptions on the max stable process itself. So in particularly, if J is a zero mean Gaussian random field, it's 3 times differentiable, and the gradient is a non-degenerate Gaussian field, then we can consider another statement which describes the topology of the solution. So in particular, what we can prove is that a finite number of the PDE will be satisfied exactly for a finite number of simply connected regions. So to give you an idea of what the implications of these results mean is, well, in the case of the physics-informed max stable process, the first result that we presented, this suggests that the proposed max stable process is going to properly extrapolate while still use the properties of the data of the PDE. However, it is less conservative than the strong solution to the PDE, which is the solution that you get by solving the max stable by solving the PDE with the max stable boundary condition itself. And on the other hand, we know exactly how many that the solution on the interior will satisfy the PDE exactly on a finite number of simply connected regions. Now we get to our numerical experiments, and what we're interested in doing is comparing the difference between the exact solution with the max stable condition, which is given right here, and the max stable solution, weakly satisfying the PDE, which we define using this operator right here. So what we do is we take some data and we fit the finite dimensional margins using the method that we described previously, the Dmax decreasing neural networks, and specifically the generative version of that. And then we compute these solutions of the PDE using the basic Feynman-Katz method. So to give you a close-up look of what this looks like, in the case where we exactly satisfy the PDE, you see that the solution is smooth since it satisfies the PDE everywhere. And this is for the exterior Dirichlet problem. So we have these circles which are considered the boundary condition. On the other hand, if we look at the max stable solution to the PDE, we see that the data is kind of clustered in a, or the PDE is not exactly satisfied on every point. And you can see these kind of lines where we can imagine that the PDE is not being satisfied on these regions. And what's more interesting, and we can repeat this for a number of different experiments. So in this case, we have 25 different experiments. We can look at the ratio of the two solutions. And indeed, as we predicted, the solution given by the exact solution with the max stable boundary condition and the max stable solution, the exact solution is bounding the max stable solution, and it bounds it by sometimes an order of 1.6 of 60% more. And then we can also visualize how the different regions are of the max stable process, where the individual regions that the dominating index is contributing in this figure right here. Now, in our second case, we're interested in real data, which we look at the heat equation in Arizona. So we have these historic data from the government that are given along these yellow squares. What we're interested in doing is interpolating the regions outside of it. So we consider two experiments, one where we consider the boundary data only, and the other one considers the exterior Dirichlet problem as done in this case right here. So for the exterior Dirichlet problem, we can see a similar set of visualizations between the max stable solution and the strong solution of the PDE. And we see again that the strong solution bounds above the weak solution, the max stable solution. In this case, is about 35% more. Can again visualize the different regions where the max stables, where the different components are dominating in the max stable case. So these are again the regions where the PDE is exactly satisfied. We do the same thing for the boundary value problem. And we see again that the data that is given by the max stable solution is bounded and above by about 20% by the strong solution. And again, look at the topology of where the components are exactly being satisfied. So the main takeaways are that we describe a framework for encoding the properties of linear elliptic PDEs into max stable processes. We prove that this framework is optimal in the sense that we request, such that the solution is the one that is both max stable and satisfies the PDE according to our defined weak solution given by this relation. And we describe the topological properties of where the PDE is satisfied exactly. Now there's two next steps, which are very important. One is we focused on the case with max stable boundary conditions, but we may want to consider the case with max stable coefficients, which is particularly interesting in the case of inverse problems. Second, we want to consider more general PDEs. So for example, we might want to consider a comparison principle rather than a strict maximum principle, as we thought. So if we have different boundary data, how do the solutions of the PDE might compare in the comparison principle? So thank you very much. And that's all for this project. Thank you.